Assalamualaikum warahmatullahi wabarakatuh. Today we will present our artificial intelligence mini project titled F1 Lap Time Prediction, a machine learning approach to simulating modern Formula One race pace. Formula One lap times are affected by many factors such as tire degradation, fuel consumption, weather condition, and the driver's performance. These factors make lap time prediction a challenging problem because the relationship between them is highly nonlinear. Okay, so to solve this problem, we developed a machine learning system that predicts Formula One lap times using historical race data. We also integrated the train model into an interactive dashboard for users. There are three objectives in this project. First, to pre-process and clean the historical Formula One dataset. Second, to develop and train a machine learning model for lap time prediction. Third, to deploy the train model into an interactive Streamlit dashboard for real-time prediction. Okay, so for our dataset, we use the Formula One World Championship dataset from Kaggle together with F1 telemetry data. We only use the races from 2019 onwards to ensure that the data represents the modern Formula One regulations. Our input features are race ID, driver ID, lap and position, while the target variable is the lap time in milliseconds. The methodology consists of 5 main stages. We first collected the dataset, then merged and pre-processed the data. After that, we selected the input features and target variable. Next, we train and evaluate the machine learning models. Finally, integrate the best model into a Streamlit dashboard for user interaction. Now, I would like to invite my teammate to continue with the AI model and the project demonstration.
For this project, we selected the random forest regressor as our final machine model. And we first compared it with the linear regression. However, Formula One data is highly nonlinear, so linear regression could not accurately capture the relationship between various variables. Random forest perform much better because it combines multiple decision trees and produces more stable and accurate predictions. Our model uses the following configuration, which are the train test split of 80% for training and 20% for testing. Random state equals 42 to ensure reproducible results, and jobs equals -1 to use all available CPU cores, and estimators equals 50 decision trees. So next, I will demonstrate our application. Move on to the most exciting part of the project, which is the live demonstration of the ultimate F1 analytics and prediction dashboard. So we built this interface using Streamlit to make our machine learning model interactive and also accessible. So let's run through a quick scenario. So on the left sidebar, users can input specific race conditions. For example, let's select Charles Leclerc. We can adjust the sliders to set him at lap 10 and also running in 5th position. As you can see on the main screen under the live lap time prediction, our random forest model instantly calculates his predicted pace down to the millisecond. And right next to it, the historical lap time spread gives us a visual histogram of Leclerc's normal racing lap distribution, allowing us to immediately see if this predicted pace is an outlier or within his average performance window. Next is the AI podium predictor. This is where our constructor handicap algorithm comes into play. So the system simulates a late race scenario, specifically lap 50 for the entire active grid. Instead of just relying on historical data, which might favor all the cars, our algorithm adjusts the predicted times based on the mechanical capabilities of the teams right now. This gives us a highly accurate and realistic prediction of who will secure the P1, P2, and P3. At the bottom, we included the driver championship standings and a custom 2020 to 2024 historical baseline. These tables filter the raw dataset to extract actual win rates exclusively for the active rate. It serves a real world benchmark so users can validate if the AI's predictions align with long-term driver consistency. That concludes the system demonstration. I will now hand it over to the next person for our next presentation.
Now I will present the project result. To evaluate the models, we use three performance metrics: means absolute error, root mean square error, and R squared score. This helps us measure how accurate our lap time prediction are. Our dashboard allows user to select the race, driver, current lap, and race position. Based on this input, the system predictions the lap time in a real time. It also shows the driver's historical lap time distribution for comparison. Other features is the AI podium predictor. It predicts the top 3 finishing driver based on the selected race conditions. The dashboard also displays the driver championship standing and historical performance analysis to help user better understanding each driver's performance. The responsible AI, our project only use publicly available data from Kaggle and Fast F1, so no personal information is collected. However, the model does not consider unexpected events such as rain, accidents, and safety cars. Therefore, the prediction should be used as a guide rather than the expect race results. In conclusion, this project successfully developed a machine learning system to predict Formula One lap times. The random forest model achieved good prediction accuracy and was successfully integrated into an interactive dashboard. In the future, we plan to improve the system by adding weather data, tire compounds, and live telemetry to make the predictions more accurate. Thank you for your attention.
Hello, Assalamualaikum. My name is Muhammad Syahrul bin Masri. My student number is 2023-627-224.
And my name is Muhammad Najam bin Hassan. My metric number is 2023680886.
For our title for this mini project is Deep Learning Based Classification of Corn Leaf Disease using Transfer Learning. So, I will go to the first part, that is introduction and problem statement. The corn leaf disease can reduce photosynthesis, plant growth, and crop yield. Manual diagnosis depend heavily on visual experience and may be slow or subjective. So why an AI solution is needed? Because we have three reasons. First, similar symptom can cause incorrect identification. Delay treatment may increase disease spread and cost. Automated screening provide faster and more consistent support. So we go to the next, that is objective. For the first objective is develop a four-class deep learning corn leaf classifier. Second, apply transfer learning and fine-tuning with mobile net. Third, evaluate accuracy, precision, recall, F1 score, loss curve, and coefficient matrix. Fourth, demonstrate deployment through a TensorFlow-like interface. And last, discuss fairness, reliability, privacy, and societal impact. For data description, we use the RoboFlow image dataset loaded in Google Colab. Total image we use is 10,048. For the training, we collect 8,793, and for the validation, 836. For the testing, we use 419. And the target classes, we collect a blight, common rice, dry leaf spot, and healthy. Okay, for the data pre-processing, we load the class folder using the flow from directory. Resize all image to 224 times 224 pixel. Process in batch of 32 image. Apply mobile net pre-process input normalization. Use category label and category cross entropy. And last, we set test generator to shuffle into false. Okay, for the methodology or workflow, first we collect the dataset acquisition download from the RoboFlow. Second, dataset organization, we train, validation, and test folder. Third, image pre-processing, that is resize and mobile net normalization. Fourth, mobile net setup, that is load pretend based without head. Fifth, classification head, this is a global average pooling plus softmax. After that, initial training, that is we freeze base and train classifier. Next, we fine tuning that unfreeze final to 20 layers. Take the evaluation, that is use the metric curve and coefficient matrix. And the lastly, we transfer transfer light deployment, that is a drag and drop prediction interface.
So here is a mobile net model architecture. We train our model to receive input 224 times 224 times 3, which is RGB image. Then mobile net features extractor, global average pooling, and dense layer we set to 4. Step 1, freeze the convolutional base and train the custom classifier. Stage 2, unfreeze the model to 20 layers and fine-tune using lower learning rate. This is to ensure the model can learn the pattern of the disease to ensure the model can differentiate type of diseases and differentiate the disease-affected leaf and the healthy leaf. So here is the training performance and confusion metric. Learning loss result. As you can see, the learning curve is decreasing, and for validation loss result also decreasing. These two graph indicate that our model losses decreased by epochs, and for accuracy result, as we can see, the result is increasing, and I believe this is around 90% of accuracy result. This indicate that by each epoch, our model can differentiate and learn the pattern of the diseases and differentiate types of diseases and healthy leaf. Next, we have confusion metrics. These metrics allowing us to visualize the model performance by seeing the model prediction and actual result. And next is key result interpretation. For healthy prediction, the model successfully predicted 100% precision and 100% recall. For common rust, the model is successfully predicted 99.21% recall and 98.44% F1 score. For blight, the model is successfully predicted 96.46% recall and 94.37% F1 score. So this is result summary, classes, precision, recall, and F1 score. Blight, Comoras, grey leaf spot, and healthy. This is the data represented in table. So for test set, we have 419 images, correct 404 images, and best class is healthy, and hardest class is grey spot. And this is our random test prediction. We collect 10 images for each class. This is our web application, and for this application we use TensorFlow Lite. Reason why we converted it to TensorFlow Lite is because as we know, TensorFlow Lite is light version of our classification model to ensure the performance and speed. So this is successful. So this TensorFlow Lite is successfully predicted healthy leaf, blight disease, gray spot disease, and common rust. And next is responsible AI, ethics, and societal impact. For responsible AI, for dataset bias is unequal performance across classes, forms, or convarieties. And proposed mitigation is use balanced and diverse images, report class level metrics. For incorrect prediction, missed diseases or unnecessary treatment. For proposed mitigation is use human confirmation and confidence threshold. And the third one is privacy and security, exposure to private API key. So the proposed mitigation is remove credential and use secure environment variable. Alright.
Okay, for the limitation and future improvement, first limitation is limited farm and variety diversity. Second, possible mild overfitting. Image only diagnose Image only diagnosed only for output classes and no extensive external field tests. For the future work, we can add rotation, flip, zoom, and brightness augmentation, collect a larger real farm dataset, compare the efficient net and ResNet, also DenseNet, tune learning rate, dropout, and trainable layers, and the last test on mobile device and in-field condition. Okay, for the conclusion for our project, the mobile net transfer learning model successfully classified ConLIF into four classes and achieved 96.42 accuracy on 419 test image. So the TensorFlow Lite interface demonstrate lightweight deployment for individual image prediction. So for the overall project, the objective were achieved, but the system should remain a preliminary decision support tool. More diverse field data, argumentation, architecture, comparison, and the real-world testing are needed before practical deployment. So that's all from us. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Ihsan bin Muhammad Nazaruddin. My metric number is 2023644108. Today, we want to present our face mask detection for mini project ETC676. Okay, now I want to show you our problem statement that we faced during project. For number one is manual mask compliance monitoring cannot scale consistently across BB and J, shift and crowded setting. Number two is no lightweight, easily deployable, the automated alternative exists for small organization without specialized hardware. Number three is unclear whether a simple custom model or a pretend approach give the better accuracy, efficiency balance. Number four is without rigorous metric-based evaluation, reliability for real world deployment cannot be established. Number five is AI systems processing facial data, risk overlooking ethical, fairness, and privacy consideration. Okay, next. This is our objective. Number one, develop an automated real-time detection system to replace unscalable manual monitoring. Or number two is a lightweight web application that runs on standard hardware, no special infrastructure needed. Number three is we compare a baseline CNN against MobileNet V2 to identify the better accuracy efficiency trade-off. Number four is we evaluate is both model with accuracy, precision, recall, F1 score, and conclusion matrix to confirm reliability. Number five, we discuss with responsible AI, fairness, privacy, and societal impact throughout the solution. Okay, next. This is our dataset overview. If you can see here, we use with math we use 3,725, and then for without mask 3,828. For data image, 7,553. We have two classes. The 70% we train and 30% is data validation. This is our pre-processing, preparing the data for resize. We standardize input dimension for the CNN, and then we normalize, we scale pixel value for stable training, and then augment, reduce overfitting, improve generalization. Number four, we split, separate training data from unseen and validation data. This is our end-to-end workflow. Datasets collection, data pre-processing, train validation split, model development, model training, model evaluation, model comparison, model deployment, and real-time detection. Now I will pass it to Pak Jufri.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Faik Jufri bin Muhammad Jalaluddin. My student ID is 2023601096. So now we will move to the part, model development part. So we usually use two model. For the model one is baseline CNN with the 95.56% validation accuracy. And the second one is MobileNet V2 with a 98.10% validation accuracy. So why MobileNet V2 was selected? So MobileNet V2 outperformed the baseline on every metric: accuracy, precision, recall, and F1 score. So for the next part is evaluation result. So if you look here, we have the MobileNet result. For the accuracy is 98.10%. For the precision is 98.51%. For the recall, 97.74%. And the last one, F1 score is 98.20%. Awareness of issue. For the first one is bias and fairness. The dataset may not equally represent all skin tone, ages, or mask type, which could cause uneven accuracy across demographic group. The second one is data privacy. The system process live facial image even without identity recognition. Consent and data retention policy must be considered. And the last one is reliability. A misdetection could create a false sense of safety if relied upon as the sole compliance check. And we move to the next part, which is responsible AI practice applied. For the first one is no identity recognition. So our system classify mask status only. It never identify who a person is. So it's a limited potential for misuse. For the next one is data privacy alignment. Deployment consideration align with data protection principles such as Malaysia PDPA. And the last one is document limitation. So model limitation and failure mode are explicitly disclosed rather than hidden. Now we move to the next part, which is a societal impact. So for the benefit part, automate health compliance screening at boarding entrance, hospital and school. The next one is reduce burden on human staff, enable consistent, tireless enforcement. Now we move to the risk to manage. For the first one, it should never be the sole basis for denying access without human oversight. The next one is facial image processing could be misused for surveillance if combined with identity recognition. Now continuous improvement roadmap. So what we remove? What can we improve for our project? Expand the dataset. Add a third class for incorrectly worn mask. Include more diverse skin tone and lighting. Next one is upgrade face detection. Replace cascade with a deep learning based detector for toggle angle. And the second one is cloud deployment. Move beyond a local machine to a cloud host app for a wider multi-location accessible. And the last one is ongoing bias audit. Periodically, we evaluate accuracy across demographic subgroup before wider rollout. So now we move to the live demonstration. Walk you through what you are seeing here. This live dashboard update in real time as the camera runs its tracking. It's tracking four things. The first one is people detected. That's how many faces the system currently sees in the camera frame. So the next is with mask and without mask. So this show how many of those detected faces are wearing a mask or not, based on what our model predict. And finally, model confidence. So this tells us how sure the model is about its own prediction. So if it say 98% above, that means the model is very confident in the result it just gave. So you see here, this me without mask, and this me with the mask. Balik. Oh, balik. Okay, so this is my friend without the mask. So the dashboard really update the actual result. Now we successfully done the live demonstration part. Now we move to the conclusion. What we achieve? In conclusion, we successfully build and compare two AI model. The first one is a custom CNN and the second one is a MobileNet V2 transfer learning model. So we successfully achieved 98.10% validation accuracy with the deploy model. So deploy a working real-time webcam application using Streamlit. And the last one, we successfully identify and address key responsible AI consideration throughout development. So that's all from us. Thank you.
Today, in this video, we will explain about our mini project entitled
Traffic sign recognition using image classification.
Okay.
First and foremost, the introduction for this project. The project background is the aim of the project to classify Malaysian traffic sign images into 5 categories, which is stop sign, no entry sign, no parking, speed limit, and others. This project belongs to the computer vision category because the system analyzes images and predicts the most suitable class.
For problem statement and objective, traffic sign contain important road information. However, recognizing sign manually from image collection can be time consuming. Our objective is to develop a simple AI prototype that can classify a traffic sign image, show confidence score, and evaluate the model using spread U-test dataset.
Okay, next, for dataset description, we use a self-collected image dataset. The images were collected manually from publicly accessible web pages found through Google Images. The training dataset contains 261 images, which is 50 for stop sign, 50 no entry sign, 50 no parking, and also 50 speed limit. But for the other images, we use 61 images. For testing, we use 100 separate images with 20 images for each class. The test images were not used during training.
Model and training, the model was trained using Google Teachable Machine. It is an image classification model based on transfer learning. The input image is resized to 2 to 4 by 2 to 4 pixels and converted into a format stable for the model. We trained the model using 50 epoch, batch size 16 and learning rate 0.001. After training, the model was exported as TensorFlow.js using model.json, metadata.json, and wave.bin.
For web application demo, the trained model was deployed in the Python Flask web application. The classifier page allows the user to upload or even drag an image. The selected image is shown as a preview. When the user clicks Run Recognition, the model predicts the class and displays the confidence score for all 5 classes. The system runs locally at 127.0.0.15000.
We go to the evaluation and result. We also create an evaluation page. The user select the test dataset folder and the system evaluate all 100 images automatically. The final accuracy is 50.5%, macro precision is 46%, macro recall is 50.5%, and macro F1 score is 46.6%. Since there are 5 classes, the random baseline is 20%. Therefore, the model performs better random casing.
For the result analysis, from the confusion matrix, the other class performs best with 70 correct predictions out of 20. The no-entry class is the weakest because many no-entry images were confused with stop or speed limit. This is mainly due to the small dataset and also the similar color to shape between some traffic signs.
Lastly, for responsible AI and conclusion, for responsible AI, we recognize that this model has limitation. The dataset may be biased because it is self-collected from online images. The model may fail under poor lighting, rain, blur, or unusual camera angle because traffic sign recognition relates to the road safety. This prototype should not be used directly for real vehicle control. In conclusion, we successfully built, deployed, and evaluated a working image classification prototype. Future work should increase the dataset size and compare the model with a custom CNN or object detection model.
That's all from us. Thank you.
I just had to let you know you're she had me, baby, she had me.
video, we will explain about our mini project entitled
Traffic sign recognition using image classification.
Okay.
First and foremost, the introduction for this project. The project background is the aim of the project to classify Malaysian traffic sign images into 5 categories, which is stop sign, no entry sign, no parking, speed limit, and others. This project belongs to the computer vision category because the system analyzes images and predicts the most suitable class.
For problem statement and objective, traffic sign contain important road information. However, recognizing sign manually from image collection can be time consuming. Our objective is to develop a simple AI prototype that can classify a traffic sign image, show confidence score, and evaluate the model using spread U-test dataset.
Okay, next, for dataset description, we use a self-collected image dataset. The images were collected manually from publicly accessible web pages found through Google Images. The training dataset contains 261 images, which is 50 for stop sign, 50 no entry sign, 50 no parking, and also 50 speed limit. But for the other images, we use 61 images. For testing, we use 100 separate images with 20 images for each class. The test images were not used during training.
Model and training, the model was trained using Google Teachable Machine. It is an image classification model based on transfer learning. The input image is resized to 2 to 4 by 2 to 4 pixels and converted into a format stable for the model. We trained the model using 50 epoch, batch size 16 and learning rate 0.001. After training, the model was exported as TensorFlow.js using model.json, metadata.json, and wave.beam.
For web application demo, the trained model was deployed in a Python Flask web application. The classifier page allows the user to upload or even drag an image. The selected image is shown as a preview. When the user clicks Run Recognition, the model predicts the class and displays the confidence score for all 5 classes. The system runs locally at 127.0.0.15000.
We go to the evaluation and result. We also create an evaluation page. The user select the test dataset folder and the system evaluate all 100 images automatically. The final accuracy is 50.5%, macro precision is 46%, macro recall is 50.5%, and macro F1 score is 46.6%. Since there are 5 classes, the random baseline is 20%. Therefore, the model performs better random casing.
For the result analysis, from the confusion matrix, the other class performs best with 70 correct predictions out of 20. The no-entry class is the weakest because many no-entry images were confused with stop or speed limit. This is mainly due to the small dataset and also the similar color to shape between some traffic signs.
Lastly, for responsible AI and conclusion, for responsible AI, we recognize that this model has limitation. The dataset may be biased because it is self-collected from online images. The model may fail under poor lighting, rain, blur, or unusual camera angle because traffic sign recognition relates to the road safety. This prototype should not be used directly for real vehicle control. In conclusion, we successfully built, deployed, and evaluated a working image classification prototype. Future work should increase the dataset size and compare the model with a custom CNN or object detection model.
That's all from us. Thank you.
I just had to let you know you're.
Okay, Assalamualaikum warahmatullahi taala wabarakatuh. My name is Abdul Samad.
My name is Ahmad Shahimi.
So today we're gonna present our mini project AI, which is student performance predictor, predicting math score using linear regression. So we go to the first slide, which is project overview. So the problem statement is Can we accurately predict student math score using demographic and academic features? So the objective of this mini project is to develop a regression model to predict math score, identify with a factor most influence performance, create a user-friendly prediction tool. So the category of this mini project is supervised regression. The algorithm we use is linear regression, and output is interactive dashboard. So next slide is, so the source that we use is Kaggle, and the dataset comprise 1,000 student record with demographic, socioeconomic, and academic performance feature. So here are some of the feature, all the feature actually: genders and race, parental level education, lunch status, standard or free, test preparation course, reading score, and writing score. So the target for this model is math score continuous range between 0 to 100. Okay. So next slide is, okay, project workflow. First, we use load data, import Kaggle CSV into the notebook, Jupyter notebook, and then we clean and process the data and handle missing value, duplicates, and outlier. The outlier we using IQR method lah. So, and then we encode and scale, use one-hot encode and standardization model for the dataset, and then train the model, feed linear regression. Okay, and then evaluate and deploy, assess metrics, and deploy to the dashboard. So next slide is data pre-processing. So we use a data quality check. So we first check if there is a missing value and there is no missing value, and check if there is a duplicate data. There is one duplicate data, and then we move it. So next is outlier handling. So we use the IQR method for this outlier handling. And then feature scaling standardization for numerical feature. So this is important for linear regression because you want to scale the number to 0 to 1. So we use a feature encoding for the categorical data. Notice features after encoding. So next slide is correlation analysis. So key insight is reading and writing score are overwhelming the strongest predictors of math performance, with correlation of 0.81 and 0.79 respectively. So socioeconomic indicators, lunch status, and gender show moderate influence, while test population has the weakest association. So a correlation between reading and writing suggests academic ability is unified latent factor. So we go to the next slide.
I will be presenting our model performance today. First, we'll look at our R-square score. For R-square, our model show an R-square score of 0.876, which is around 87.6% of variance in math score can be explained using this model. And then next we will go to the MAE score, which our model show 4.55. It means that the average prediction error of around 4 to 6, 4.6 point as compared to a real score. After that, we go to the RMSE, which show 5.65. RMSE penalized larger error, still well within acceptable range. The model demonstrates excellent predictive accuracy with low mean, absolute error, and high coefficient of determination, which means strong evidence of well-fitted linear model. As you can see at graph on the right side, on the top side, it shows that the model show the prediction are around the line, which mean is accurate. At the bottom chart show the residual plot. What we watch to see over here is randomness. There's no discernible pattern, which show that this model are not biased. Okay, next slide. For this slide, model comparison, the value of academic feature. As you can see from the graph show the comparison between the first model that we create and the second model. For the first model, as you can see, the dot is all over the place. It doesn't really align with the line, with our target line, as compared to the second model. So what the number tell us is that excluding reading and writing score drastically reduce the model performance, confirming their central role as predictor. And now I'm going to talk about our responsible in AI. First, we'll talk about bias in our data. In the data, the gender show is plus 13 mark advantage, which could reflect societal bias, not ability. The data set also lack diversity, which means that the prediction may not apply to all student groups. And then we talk about data privacy, because we're playing with mostly underage students. It means that the student data is quite sensitive and must comply with the FERPA or the student privacy law. So in order for us to use it in our AI, we need to anonymize the data before we use it. And then we have the human oversight. This we need to make sure that teacher or parent know that this is a support tool and not a replacement for teacher. And despite the AI can help in education, an educator or teacher will have the final decision, not the AI. And then we need to know who benefit and the risk of using this. The teacher get early warning for struggling student, and the risk for that is the teacher could misuse or unfairly label a student based on our AI prediction. All right, next. And next, going to talk about our interactive dashboard. Uh, this dashboard was made using Streamlight. The reason we choose it because it is a lightweight, user-friendly web application and enable educator and student to interact with the model in real time. And the way interactive dashboard work is that first, we input the student demographic and prior score. Next, we adjust reading and writing score to explore scenario. Third, we will receive instant math score prediction. And then fifth one, it will compare result against similar student profile to make sure that the results are as accurate as possible. Right, next slide. And as a conclusion for our project is that this model show an accurate prediction with an R-square of 87.6%. The key factor identified is the important thing that this model need to identify the correct prediction is reading and writing score, which are the dominant predictor. The tool we use interactive Streamlight dashboard for user, and the ethic consider is that we need to make sure to be careful around bias, privacy, and human oversight. And for future improvement, we need to add more data like attendance, study hour, or teacher quality. And then we need to test it against other algorithm like random forest or XGBoost. And then we also need to build in a bias monitoring system for this. All right, that is all for us. Thank you.
Hello, my name is Ryan Isaiah Harry with student number 202368076.
My name is Tengku Ifaikal bin Tekong Fuad. My student number is 20236372882. So our project title is called Fruit Detection using YOLO V8 with a flash-based dashboard.
So first and foremost, we choose fruit detection because it is a very valuable computer vision task because it is available in a lot of application, especially automation, smart retail, inventory support, and also works with educational AI demonstration. So we are using YOLO V8 to detect our three dataset, which is from apples, bananas, and orange in a real time and present the result through a flash-based dashboard. So first of all, our problem statement is the initial model, it is misclass non-fruit objects. For example, can be hands, table, chair, and then as fruit due to limited training diversity. So false positive reduce reliability in real world environment. So our solution is to add negative background image to the dataset so it can improve the performance more. So first of all, our objective is to detect apple, banana, and orange using YOLO V8 for now. So and then we will improve the robustness by adding more negative and background image to the dataset to increase the performance. And then we also will evaluate model performance using precision recall, MAP, and confusion matrix. This will deploy the model in a flash dashboard with a live webcam. So the tools we are using, RoboFlow, which is where most of our dataset of images are from, and then we're using Google Colab to develop the AI model, and we are using YOLO V8 to train, and then Python, Flash, OpenCV, and VS Code to do the overall dashboard, and then we use our hardware, which is laptop plus webcam. And this is our dataset and data preparation. The source is RoboFlow Universe, and we have a bunch of dataset which is with the apple, banana, and orange, each with their own 100 image in the dataset. And yeah, we move on to the methodology.
So first, we collect and prepare dataset, which is a positive plus negative image, which is we use a real negative image, and then annotate and manage the dataset using RoboFlow. Third, we train using YOLO. We train using Google Colab, but the model is YOLO V8, and then validate anti-model, which is have hyperparameters and epoch, evaluate precision, recall, MAP50, and confusion matrix, and then export base PT to the VS Code, and then we output to the dashboard. Okay, so we training the model in the Google Colab. Okay, and then we show the hyperparameters and epoch, which is our training curve using 100 epoch, and then okay, so the result we get is precision with a 0.89, which is 89%, recall 90%, MAT50 95%, MAT50 95 67%. So the summary we got apple with the average of 80%, banana with the 90%, orange with the 80%. Okay, so this is the confusion matrix. Okay, so this is our dashboard that output. So it detect banana, apple detection, orange, and mixed fruit. Okay, so the live testing result. Okay, we show the live testing result next. Okay, so this is the system architecture. First webcam, and then YOLO V8 Nano, and the flash server to the dashboard. Alright.
So AI is responsible in also a lot of ethics and limitation. That's why we are looking into the privacy, which is no images are stored permanently. The system process video ephemerally for real-time inference. So it is designed for educational, research, and productivity application. It is not intended for surveillance or misuse. And for transparency, the model decision may vary with lighting, occlusion, and unseen object. The final decision should be verified by human in critical application, and the limitation is performance depends on the dataset quality and also environmental condition. The model may still produce occasional false positive. So for conclusion, this project is successful in demonstrating the real-time fraud detection using YOLO V8 on a custom dataset of apple, banana, and orange. So we will be going to the demonstration.
Okay, wait. Before the demonstration, we also have a test result. So this is the test. So first, the apple, the banana, and the mixed fruit. So this is our negative test, and then orange. Okay. Okay. So we move to the demonstration part. So first, we detect the banana. This banana. And then apple, and then orange, and then mixed fruit. Alright. So each also output also have a detection summary, which is three fruit detect, one apple, one banana, one orange. Okay. That's all from us. Thank you.
Thank you.